Right now, you are standing on a surface that has witnessed civilizations rise and fall in ways you cannot imagine. Beneath your feet lie layers of compressed earth, each stratum a chapter in a story far older and stranger than the history books dare to tell. We call this our home. We call it Earth, but we have never truly understood what came before us. Tonight we will journey into the deepest mysteries of our planet's past and discover that everything we thought we knew about human uniqueness, about our place in time, and our role as the first builders of civilization is just the beginning of a far more complex tale. If you enjoy this journey into Earth's hidden history, come along, prepare yourselves, we begin. Archaeologists often describe the moment they first comprehend deep time. They stand in an excavation pit, brush in hand, carefully exposing artifacts that have not seen daylight for thousands of years. Pottery shards that once held water for families long forgotten. Stone tools shaped by hands that turned to dust before the pyramids were even conceived. They label each find, photograph its position, and slowly piece together the story of ancient peoples. But here is what keeps them awake at night. They are only seeing a fraction of what once existed. This reveals something profound about preservation that we rarely consider. Time erases almost everything. From the moment an object is abandoned, forces begin working to destroy it. Rain dissolves, bacteria consume, geological processes grind and compress. What seems permanent when you hold it in your hand proves impossibly fragile when measured against millions of years. Consider this. If you buried a modern smartphone in your backyard today, how long would it survive? The glass screen would shatter from ground pressure within decades. The plastic casing would begin breaking down within centuries. The circuit boards would corrode. Within a few thousand years, almost nothing recognizable would remain. And that represents one of our most sophisticated technologies, vanishing in a geological eye blink. Now, imagine pulling back further. At 10,000 years, almost all traces of contemporary civilization would have degraded beyond recognition. At 100,000 years, even our largest structures would crumble to unidentifiable rubble. At 1 million years, the very rocks would have shifted, been buried, been thrust upward again, weathered away by wind and rain into entirely new formations. This preservation challenge works both ways, though. Just as our artifacts will someday vanish, anything that existed in Earth's deep past would face identical destructive forces. That concrete foundation beneath your house will not last forever. Neither would any foundation built by hypothetical predecessors millions of years ago. The isolation created by deep time is staggering. If another civilization had thrived on Earth 100 million years ago, at the height of the Cretaceous period, their entire existence would have been ground to dust by geological processes we cannot prevent or reverse. Continental drift would have scattered their ruins. Subduction zones would have dragged their cities into the mantle. Erosion would have worn their monuments to sand. But we are not powerless in this vastness. We search through it as investigators examining a crime scene where almost all evidence has been destroyed. We examine rocks, we analyze chemical anomalies, and we look for patterns that should not exist. We hunt for shadows of the impossible. The rocks beneath our feet began a journey that makes every human exploration look like a stroll around the block. Stone formations from the Cretaceous period, laid down 100 million years ago, have been subjected to heat, pressure, and chemical transformation that few human-made objects could survive. 100 million years. Let that number settle in your mind. 100 million years. If you could somehow live one human lifetime per second, it would take you over 1,200 years of non-stop living just to experience that time span subjectively. 1,200 years of entire lifetimes compressed into seconds. This reveals the true scale of Earth's history. Fossils that appear as delicate impressions in stone actually represent creatures that lived for millions of years before their final remains were preserved. They look fragile only because of the breathtaking time periods involved. Deep time stretches so far before the emergence of humans that our entire species, from first stone tools to space stations, represents less than 0.003% of Earth's total history. Our planet contains roughly 4.5 billion years of history. Some rocks have survived from nearly the beginning, carrying chemical signatures from an Earth that looked nothing like our current home. Each one holds clues about past conditions, but the record grows increasingly fragmentary the further back we look. Consider this: the fossil record preserves perhaps 0.01% of all species that have ever lived, maybe less. The vast majority of life that has walked, crawled, swum, or flown on this planet left no trace whatsoever. Soft-bodied organisms rarely fossilize. Small populations in remote areas vanish without record. Even bones typically decay completely within thousands of years unless very specific conditions preserve them. This creates a strange situation. We live on a planet with a history so vast that we can never see more than tiny fragments of it. We experience Earth like archaeologists examining a burned library, able to read scattered pages, but never able to reconstruct the complete volumes that once existed. Imagine holding a single grain of sand between your fingers. Feel its tiny weight. Notice how it barely registers against your skin. This grain measures roughly 1 millimeter across. You could lose it in the carpet and never find it again. Now let this grain of sand represent your entire lifespan. Every memory, every experience, every moment from birth to death gets compressed into this tiny speck. A whole human life shrinks down to something you could accidentally inhale. On this scale, how long would recorded human history be? All of civilization, from the first written records in Mesopotamia to the present day, would span about 5 grains of sand, laid end to end, 5 millimeters, less than a quarter inch. But we are just getting started with this exercise. If a single grain represents a human lifetime, the entire history of anatomically modern humans, roughly 300,000 years, would stretch about 4 meters. The length of a small car, the time since dinosaurs went extinct, would extend 85 kilometers. You could not walk it in a day. The age of dinosaurs themselves would span 230 kilometers of sand grains, the distance from one city to another. And the age of Earth, that would require a line of sand grains stretching 5,900 kilometers, the distance from New York to London, an entire ocean of individual human lifetimes laid end to end. This scale model reveals something shocking about time. The periods we think of as ancient, the Roman Empire, the Egyptian pyramids, even the first human tools, represent practically nothing compared to Earth's total history. We exist in a tiny sliver of time at the very end of an almost incomprehensible story. Our entire species has existed during less than 0.007% of Earth's history. Civilization represents about 0.0002%. Written history, a mere 0.0001%. We are newcomers who arrived at the party moments before closing time, trying to piece together what happened during the preceding days of festivities. Right now, as you sit reading these words, you are spinning through space on a planet that has kept secrets longer than any civilization has existed. You are not simply riding a ball of rock and water. You are traveling on a geological archive so vast that reading it completely would require more than the entire history of human existence. What preserves these ancient secrets? The answer involves something far more dynamic and violent than most people imagine. Our planet constantly renews itself through processes that destroy and create in equal measure. Tectonic plates drift across the surface at speeds measured in centimeters per year. Volcanoes erupt, laying down new rock. Erosion wears away mountains. Sediments accumulate in layers that eventually compress into stone. This geological recycling operates on a timescale of hundreds of millions of years. The Atlantic Ocean is currently widening at about the same rate your fingernails grow. This seems insignificant until you consider that over 200 million years, this process has opened an entire ocean between continents that once touched. But what exactly does this geological machinery do to evidence of the past? The answer involves something so thorough that it challenges every assumption about what can be preserved. Subduction zones, where one tectonic plate slides beneath another, actively drags surface material back into Earth's mantle. Over millions of years, rocks that once formed the ocean floor get pulled down into zones where temperatures exceed 1000 degrees Celsius. Everything gets melted, mixed, and eventually recycled as new volcanic rock somewhere else. This creates the ultimate evidence destroyer. Any surface features, cities, roads, monuments, industrial sites built on oceanic crust would eventually be dragged into a subduction zone and completely obliterated. The ocean floor you see today is nowhere older than 200 million years. Everything that existed before that point has been recycled through the mantle. Continental crust survives longer because it is less dense and resists subduction, but even continents face relentless erosion. Mountains rise through tectonic collisions, then spend tens of millions of years being worn away by wind and water. The Appalachian Mountains once stood as tall as the Himalayas, but have been eroding for 300 million years. They have lost thousands of meters of elevation to forces that never rest. For most of human history, we believed Earth's surface was static and unchanging. Mountains had always stood where we found them. Oceans had always filled their current basins. Continents had never moved. This made sense from direct observation. We could feel no motion. We observed no dramatic changes during human lifetimes. This comfortable assumption lasted until geologists developed better tools and started measuring things more carefully. First, they discovered that fossils of identical species appeared on continents now separated by vast oceans. Then they found matching rock formations on opposite sides of the Atlantic. Evidence mounted that continents had once been joined and had somehow drifted apart. In the 1960s, scientists finally understood the mechanism. Earth's surface consists of massive plates that float on the semi-molten mantle beneath. These plates move independently, colliding to form mountains, pulling apart to create new oceans, and sliding past each other along violent fault lines. The entire surface operates like a slow-motion conveyor belt, constantly recycling material through the system. This discovery revolutionized geology and created a new problem for archaeology. If the surface constantly recycles itself, what happens to evidence of ancient surface-dwelling civilizations? In 2018, two scientists published a thought experiment that sent ripples through both the scientific and popular imagination. Gavin Schmidt, director of NASA's Goddard Institute for Space Studies, and Adam Frank, an astrophysicist at the University of Rochester, posed a deceptively simple question. If an industrial civilization had existed on Earth millions of years ago, what evidence would remain today? They called their thought experiment the Silurian hypothesis, named tongue-in-cheek after an alien race from the British science fiction show Doctor Who. The purpose was not to argue that ancient civilizations actually existed, but to explore how we would detect such a civilization if it had. Their conclusion proved both fascinating and troubling. Almost no direct evidence would survive. Think about what defines our current industrial civilization. Cities built from concrete and steel, roads paved with asphalt, massive structures like dams and skyscrapers, mountains of plastic waste, the chemical signatures of fossil fuel combustion, synthetic materials that never existed in nature. Now apply deep time. Concrete degrades within thousands of years, steel corrodes, asphalt weathers away. Even our largest structures would crumble to unidentifiable rubble within tens of thousands of years. After 1,000,000 years, almost nothing recognizable would remain at the surface. Plastic might last longer in certain conditions, but even these durable polymers eventually break down through photodegradation and bacterial action. The much-discussed Pacific garbage patch would disperse and degrade. Give it a few million years, and the plastic particles would break down completely or become so widely scattered in ocean sediments that detecting them would require knowing exactly where and how to look. What about our chemical signatures? Surely the billions of tons of carbon dioxide we have released would leave permanent marks. Here the picture becomes more complex. Yes, we are creating a spike in atmospheric carbon, but the geological record shows numerous periods of rapid climate change driven by volcanic activity, asteroid impacts, and other natural causes. Distinguishing an ancient industrial civilization's carbon pulse from these natural events would be extraordinarily difficult after millions of years of geological mixing and chemical transformation. Schmidt and Frank identified a few potential signatures that might persist. Synthetic molecules, certain industrial chemicals might persist in trace amounts in sedimentary rocks. CFCs, plutonium isotopes from nuclear testing, and other artificial elements could theoretically leave faint signals. But detecting parts per billion concentrations in rocks millions of years old would require extraordinary luck and precision. Fossil fuel depletion, an ancient industrial civilization would presumably have extracted and burned available fossil fuels, creating underground voids or altered geological formations. But over millions of years, these voids would collapse and refill. The evidence would become ambiguous at best. Unusual isotope ratios, nuclear technology might leave lasting signatures in the form of unusual isotope distributions. But natural nuclear reactors have occurred in geological history. The Oklo reactors in Gabon operated naturally 2 billion years ago, complicating any interpretation. Mass extinctions. Industrial activity could trigger extinctions through habitat destruction, pollution, or climate change. But the fossil record shows 5 major mass extinctions and numerous smaller ones, all attributable to natural causes. Distinguishing an ancient civilization-caused extinction from natural catastrophes would be nearly impossible. The thought experiment revealed something profound. The absence of evidence is not necessarily evidence of absence when dealing with timescales of millions of years. Earth's geological processes are so effective at recycling and destroying surface evidence that even a globe-spanning industrial civilization could vanish almost without trace. This does not mean ancient civilizations existed. It means that certain types of questions become scientifically unanswerable beyond a certain time horizon. We live on a planet that actively erases its own history. Despite the challenges of deep time preservation, the geological record occasionally preserves puzzles that resist easy explanation. These anomalies do not prove the existence of ancient civilizations, but they remind us that Earth's history contains chapters we have not fully read. Consider the Cambrian explosion, a period roughly 540 million years ago when complex multicellular life suddenly appeared in the fossil record in stunning diversity. For billions of years before this event, life remained predominantly simple: bacteria, algae, and basic multicellular organisms. Then, in a geological eye blink of perhaps 20 million years, most major animal body plans emerged. This rapid diversification has puzzled scientists for decades. What triggered such explosive evolutionary innovation? Was it rising oxygen levels, a change in ocean chemistry, the development of predator-prey relationships, or something else entirely? Some researchers have proposed that the Cambrian explosion might represent life rebounding after a previous global catastrophe. If Earth experienced a massive extinction event that wiped out nearly all complex life, the vacant ecological niches would allow rapid evolutionary experimentation among survivors. But what could cause such a complete reset? The Permian Triassic extinction event, which occurred 252 million years ago, offers a sobering example. This extinction killed approximately 96% of all marine species and 70% of terrestrial vertebrate species. It represents the closest life on Earth has come to complete annihilation. The causes likely involved massive volcanic eruptions in Siberia that released enormous amounts of greenhouse gases, but the full story remains debated. Could an even more ancient extinction have preceded the Cambrian explosion? If so, what would have caused it? Volcanic activity, an asteroid impact, or something else entirely? The geological record contains other curiosities. The boring billion. Between 1.8 and 0.8 billion years ago, Earth's evolution seemed to stall. Life remained predominantly simple despite having already invented eukaryotic cells and sexual reproduction. For 1 billion years, longer than the entire history of complex life since, nothing much happened. Why? What kept evolution in a holding pattern for so long? The Proterozoic puzzle. Evidence suggests that Earth experienced several snowball Earth events when the entire planet froze over, with ice extending to the equator. These global glaciations should have extinguished almost all life, yet somehow organisms survived and rebounded. Where did they endure? How did they maintain genetic diversity through these apocalyptic bottlenecks? The Great Oxygenation Event. About 2.4 billion years ago, oxygen-producing cyanobacteria transformed Earth's atmosphere from essentially oxygen-free to oxygen-rich. This represented the most dramatic chemical change in our planet's surface environment, but the transition did not happen smoothly. Oxygen levels seem to have spiked, then crashed, then gradually risen again. What caused these fluctuations? The rare earth elements. Certain geological formations contain unusual concentrations of rare earth elements in patterns that do not match typical geological processes. While most have natural explanations involving hydrothermal activity or unusual weathering conditions, a few remain incompletely understood. None of these anomalies require ancient civilizations to explain them, but they illustrate an important point. Earth's deep history contains complexity that we have not fully unraveled. The geological record is incomplete, often ambiguous, and occasionally contradictory. If we accept, purely for the sake of speculation, that an ancient advanced civilization might have existed, one question becomes paramount. How far back could such a civilization have existed while still leaving detectable traces? The answer depends on what counts as detectable and what level of technology we are discussing. Let us work backward from the present, 10,000 years ago. At this timescale, we would expect to find abundant evidence of any civilization comparable to our own. Stone structures would survive, metal artifacts would still be recognizable, even if heavily corroded. Pottery would remain intact. Agricultural impacts on landscapes would be visible. We find extensive evidence of actual human civilizations from this period, so any additional advanced civilization would be glaringly obvious. 100,000 years ago, direct evidence becomes scarcer but should still exist. Large stone structures might survive in recognizable form. Engineered landscapes would leave traces. Mining operations would create distinctive geological signatures. We find evidence of anatomically modern humans from this period, including tools, controlled fire use, and burial practices. An industrial civilization would leave far more dramatic traces than we observe. 1 million years ago, most surface structures would be heavily degraded or buried under sediment. However, large-scale engineering projects like dams or canals might still show up as unusual topographical features. Mining operations would leave distinctive underground voids or tailings. Chemical contamination from industrial processes might persist in sediment layers. The fact that we do not find such evidence places constraints on what could have existed. 10 million years ago, we enter the zone where the Silurian hypothesis becomes relevant. Surface structures would be completely eroded. Only the deepest mines might leave ambiguous traces. The main potential evidence would come from unusual spikes in carbon or other isotopes in sediment cores, artificial radionuclides in ancient rock layers, anomalous extinction patterns in the fossil record, unexpected depletions of fossil fuel deposits 100 million years ago. We reach the practical limit of detectability for most evidence. Continents have substantially rearranged. Much of the ocean floor has been recycled through subduction zones. Erosion has worn away kilometers of surface rock. Even dramatic environmental changes become difficult to distinguish from natural variations. This represents the time of the dinosaurs, creatures that left abundant fossils but no evidence of technology or civilization despite dominating Earth for over 160 million years. 1 billion years ago. At this point, detection becomes nearly impossible with current technology. the fossil record becomes sparse. Geological processes have transformed or destroyed most surface rocks from this period. Climate and atmospheric conditions were substantially different. If a civilization existed here, we would likely never know. This analysis reveals that there exists a detectability window roughly spanning the past 10 million years, where we could plausibly expect to find evidence of an advanced civilization if one had existed. The fact that we have not found such evidence provides strong constraints on what could have occurred during this period. Beyond 10 million years, the question becomes increasingly speculative because the evidence would be increasingly ambiguous or destroyed. This does not mean ancient civilizations existed, merely that scientific certainty becomes harder to achieve when dealing with truly deep time. Let us consider a different question. Could intelligence and civilization have evolved multiple times on Earth independently of humans? What would be required for such a scenario? Intelligence, as we define it, requires certain prerequisites. Brain complexity. Sophisticated cognition requires relatively large brains with complex neural architecture. On Earth, this has evolved independently in several lineages. Primates, cetaceans, elephants, corvids, and cephalopods all show varying degrees of intelligence. Brain size, relative to body size, encephalization quotient, provides a rough measure of potential cognitive capacity. Manipulative appendages. Building technology requires the ability to manipulate objects precisely. Primates have hands, elephants have trunks, octopuses have flexible arms, corvids have beaks and feet. Each lineage has found different solutions to the manipulation problem. Social structures. Most intelligent species are highly social. Language, culture, and accumulated knowledge typically require groups that can communicate and transmit information across generations. Environmental pressure. Intelligence is metabolically expensive. Brains consume disproportionate amounts of energy. Evolution favors intelligence only when the benefits outweigh the costs. This typically requires environments where problem-solving ability provides significant survival advantages. Time. Evolution of complex traits requires millions of years. Human-level intelligence required tens of millions of years of primate evolution, plus specific environmental pressures on our lineage. Given these requirements, which Earth lineages might have potentially developed civilization-building intelligence in the distant past? Dinosaurs. Despite dominating Earth for over 160 million years, dinosaurs showed limited evidence of increasing intelligence over time. Some species like Troodon had relatively large brains for their body size and grasping hands, but none approached the cognitive complexity of modern great apes. Most dinosaurs had brain structures optimized for instinct and basic sensory processing rather than abstract reasoning. Marine reptiles. Prehistoric seas contained intelligent predators like ichthyosaurs and plesiosaurs. However, building technology underwater presents severe challenges. Fire cannot burn. Metallurgy becomes impossible. Electronics are problematic. An aquatic civilization would face fundamental constraints that make technological development extremely difficult. Early mammals. Mammals existed alongside dinosaurs but remained small and relatively simple until after the Cretaceous-Triassic extinction 66 million years ago. During the dinosaur age, mammals occupied ecological niches similar to modern rodents and shrews, important but not candidates for civilization building. Ancient insects. Some prehistoric insects grew to enormous sizes when atmospheric oxygen concentrations were higher. However, insect brain architecture fundamentally differs from vertebrate brains. No insect lineage has evolved intelligence approaching even the level of modern birds, and the constraints of their body plans make this unlikely. Octopus ancestors. Modern octopuses show remarkable intelligence despite their short lifespans and lack of social structure. Their Cambrian ancestors were much simpler. While it is theoretically possible that an ancient cephalopod lineage could have evolved advanced intelligence, no fossil evidence supports this, and the marine environment presents the technological constraints mentioned above. This analysis suggests that while intelligence has evolved multiple times on Earth, the specific combination of high intelligence plus manipulative appendages plus suitable environment plus sufficient time has been rare. Humans represent the first lineage on Earth to cross the threshold where abstract reasoning, tool use, and social structure combined to enable cumulative technological development. Of course, this assumes we understand all the major lineages in Earth's history. The fossil record preserves only a tiny fraction of species. Could there have been an intelligent lineage that left no fossils? In 2007, Carol Cleland and Shelley Copley published a provocative paper proposing that Earth might host a shadow biosphere, forms of life descended from a separate origin than all known organisms. These hypothetical organisms would use different biochemistry, possibly different genetic molecules instead of DNA, and would have evolved completely independently of familiar life. Why might such alien Earth life exist? The early Earth was chaotic, bombarded by asteroids, covered in volcanic activity, with dramatically different atmospheric chemistry than today. Life might have originated multiple times under varying conditions. Most lineages would have gone extinct, but perhaps one alternative form of life persisted in extreme environments where it faced little competition from DNA-based organisms. Where might we find shadow life? Cleland and Copley suggested several possibilities. Deep underground. Kilometers beneath the surface, microbes live in rock pores, deriving energy from chemical reactions rather than sunlight. These environments remain poorly explored. Alternative biochemistry might persist here. Extreme environments, highly acidic waters, hypersaline lakes, or deep sea vents might harbor organisms too different from conventional life for our standard detection methods to identify. In plain sight, shadow life might exist among us, but our molecular analysis techniques are designed to detect DNA, RNA, and familiar proteins. If organisms use different genetic molecules or proteins built from different amino acids, standard genetic sequencing would simply miss them. We would literally not see them because we are not looking for them. The shadow biosphere hypothesis remains highly speculative. Most biologists consider it unlikely given the success of DNA-based life at filling every available niche. However, the possibility that we might be overlooking truly alien life on our own planet reminds us how much we still do not know about Earth's biodiversity. Now extend this thinking to deep time. Could a shadow biosphere have included intelligent species in the distant past? Could a completely separate tree of life have produced civilization builders that left no traces we would recognize? This pushes speculation to its limits. Without DNA, without familiar proteins, without standard biological markers, such creatures would be almost invisible to paleontology. Fossils form when organisms leave mineralized remains. If shadow life used completely different biochemistry, even its fossilization would differ from anything we recognize. This represents the boundary of scientific speculation versus pure fiction. We can imagine such scenarios, but we have no way to test them, no evidence to examine, and no theoretical framework to make predictions. At this point, we have left science behind and entered the realm of imaginative possibility. Let us approach this question from a different angle. Given what we know about evolutionary timescales and the history of Earth, how many chances have there been for intelligence to evolve? Earth formed approximately 4.5 billion years ago. The first evidence of life dates to at least 3.7 billion years ago, perhaps older. This means life emerged relatively quickly after Earth's surface cooled enough to support liquid water. Simple, single-celled life dominated for the next 3 billion years. Eukaryotic cells, cells with nuclei, appeared roughly 2 billion years ago. Multicellular life emerged around 600 million years ago. Complex animals evolved 540 million years ago during the Cambrian explosion. Animals colonized land about 400 million years ago. This timeline reveals something striking. Each major transition in complexity required hundreds of millions of years. Evolution does not rush toward intelligence. For most of Earth's history, bacteria and algae were the dominant life forms. perfectly adapted to their environments and facing no evolutionary pressure to develop brains. When complex animals finally evolved, most lineages invested in other survival strategies: speed, armor, venom, camouflage, reproductive rate. Intelligence remained a rare and expensive option that few lineages pursued. Since the Cambrian explosion 540 million years ago, we can identify several distinct epochs separated by mass extinctions: Cambrian, Ordovician, Silurian, 540 to 420 million years ago. Marine invertebrates dominated. The most sophisticated organisms were primitive fish, no candidates for intelligence beyond basic instincts. Devonian Carboniferous, 420 to 300 million years ago. Fish diversified. Amphibians colonized land. Insects grew large. Still no signs of advanced intelligence. Permian, 300 to 252 million years ago. Reptiles became dominant on land. Synapsids, mammal ancestors, diversified. Then the Permian-Triassic extinction nearly ended everything. Triassic, Jurassic, Cretaceous, 252 to 66 million years ago. The age of dinosaurs. Mammals remained small. Birds evolved. Dinosaurs showed some intelligence but never reached human-level cognition despite having 160 plus million years. Cenozoic, 66 million years ago to present. Mammals diversified after dinosaurs went extinct. Primates evolved. Humans appeared in the last few million years. This history suggests that intelligence comparable to humans has evolved exactly once in Earth's 4.5 billion year history, despite multiple opportunities. This could mean intelligence is extremely unlikely to evolve. The specific conditions that favored human intelligence are rare. Intelligence has evolved multiple times, but left no trace. We are looking for the wrong evidence. The first two explanations align with mainstream scientific thinking. The third remains possible but unsubstantiated. The fourth opens doors to speculation. Let us be more specific about what an industrial civilization would leave behind. Our current civilization has existed in industrial form for roughly 200 years. In that brief time, we have altered atmospheric chemistry measurably created thousands of synthetic chemical compounds that never existed naturally, spread plastic particles to every ocean, detonated nuclear weapons, leaving radionuclide signatures, extracted billions of tons of fossil fuels from underground reshaped landscapes through mining, agriculture, and urbanization, driven numerous species to extinction, increased global temperatures, acidified oceans. Each of these changes leaves potential signatures in the geological record. The question is, how long would these signatures remain detectable? Atmospheric changes. Our carbon dioxide emissions are creating a spike in atmospheric CO2 that will be measurable in ice cores and sediment records for hundreds of thousands of years. However, after millions of years, this spike would be difficult to distinguish from natural climate variations unless researchers knew exactly what to look for. Synthetic compounds, plastics, pesticides, pharmaceutical compounds, and industrial chemicals are spreading globally. Some will persist in sediments. However, chemical bonds break down over time through oxidation, bacterial action, and thermal decomposition. After millions of years, only the most stable compounds would remain, likely in trace concentrations requiring sophisticated analysis to detect. Radionuclides. Nuclear testing has released artificial isotopes like plutonium-239 and cesium-137 into the environment. These will remain detectable for thousands to hundreds of thousands of years depending on their half-lives. However, natural background radiation and cosmic ray interactions create many of these same isotopes in small amounts. After millions of years, our nuclear signature would fade into the noise. Fossil fuel depletion. We have extracted enormous quantities of coal, oil, and natural gas. This creates underground voids and altered geological structures. However, over millions of years, these voids would collapse, fill with sediment, and be transformed by geological processes. The evidence would become ambiguous. Landscape modification. Our cities, roads, mines, and agricultural fields dramatically alter Earth's surface, but erosion works constantly. Within thousands of years, abandoned cities become buried or eroded. Within millions of years, even our deepest mines would be compressed, deformed, or destroyed by tectonic activity. Extinction event. We are currently driving species extinct at rates 100 to 1,000 times higher than natural background rates. This will appear in the fossil record as a sudden loss of diversity. However, distinguishing a human-caused extinction from natural causes, asteroid impact, volcanic activity, climate change, would be difficult for future geologists examining rocks millions of years old. Ocean acidification. Our CO2 emissions are acidifying the oceans, which will affect which organisms can build shells and skeletons. This will appear in the fossil record as a shift in marine community composition, but similar shifts have occurred naturally in the past. The pattern is clear. Our industrial civilization will leave signatures, but these signatures will degrade, become ambiguous, and eventually fade to levels that might be difficult to detect or interpret millions of years in the future. This creates an asymmetry in our knowledge. We can be confident that no industrial civilization existed in the past few million years because we would see their signatures clearly. But beyond about 10 million years, the evidence becomes increasingly uncertain. We have journeyed through deep time, examining the evidence, considering the possibilities, and confronting the limits of what we can know about Earth's ancient past. What can we conclude from this thought experiment? First, the absence of evidence for ancient civilizations is not surprising, given the destructive power of geological time. Earth actively erases its own history through tectonic recycling, erosion, and chemical transformation. Even if advanced civilizations had existed tens or hundreds of millions of years ago, detecting their remains would be extraordinarily difficult. Second, the fossil record and geological evidence provide strong constraints on what could have existed. We have extensive evidence of life throughout Earth's history. That life shows a continuous progression from simple to complex without sudden jumps that would indicate the intervention of advanced intelligence. The lineages that could have developed civilization-level intelligence are few, and none show evidence of having done so except humans. Third, certain types of evidence would persist even across deep time. Large-scale geochemical changes, unusual isotope distributions, and dramatic extinction events all leave lasting marks. The fact that we do not find such anomalies that cannot be explained by natural processes suggests that any ancient civilizations, if they existed, were either too brief to leave lasting marks, too limited in scale to create global signatures, so different from us that we would not recognize their traces, non-existent. The most parsimonious explanation, the one that requires the fewest unsupported assumptions, is that humans represent Earth's first civilization-building intelligence. We evolved in the right place at the right time with the right combination of traits. We are not usurpers or successors. We are the first, but possibility remains distinct from certainty. Science deals with evidence and probability, not absolute proof. The deep time before 10 million years ago represents a realm where our knowledge becomes increasingly uncertain. Could something have existed that we would never detect? Perhaps, but without evidence, such speculation remains in the realm of imagination rather than science. What does this mean for us as we contemplate our place on this ancient planet? It reminds us that we exist on a world with a history far deeper and stranger than we can fully comprehend. Earth has witnessed catastrophic extinctions, dramatic climate shifts, the rise and fall of countless species, and transformations that would make our own industrial revolution look like a minor footnote. We are passengers on a planet that was ancient before we evolved, that will continue long after we are gone, and that keeps its deepest secrets locked in layers of stone we can only partially read. Perhaps the most profound insight from this exploration is not about ancient civilizations at all. It is about the nature of knowledge itself. There exist questions that science cannot definitively answer. not because of current limitations in our tools or methods, but because the universe has destroyed the evidence we would need. Deep time acts as an erasure mechanism more thorough than any cover-up, more complete than any conspiracy. This should inspire both humility and wonder. Humility because we must accept that some questions will remain forever unanswered. Wonder because Earth has proven itself capable of producing at least one civilization-building intelligence, which means the raw materials for consciousness, technology, and culture exist in the very fabric of planetary evolution. The Fermi paradox famously asks, if intelligent life is common in the universe, where is everybody? The galaxy is billions of years old. Even modest rates of interstellar travel should have produced obvious signs of alien civilizations. Yet we detect no alien megastructures, no radio signals clearly of intelligent origin, no evidence that anyone else is out there. One proposed solution to the Fermi paradox suggests that intelligent civilizations inevitably destroy themselves shortly after developing advanced technology. Nuclear weapons, climate change, artificial intelligence, or engineered pandemics might represent insurmountable challenges that no civilization survives for long. If this great filter exists, it raises an uncomfortable question. Have we already passed through the filter, or does it still lie ahead? Our exploration of Earth's deep time suggests a related question. Could Earth itself have experienced multiple attempts at intelligence, with each attempt ending in extinction before leaving lasting traces? Could our planet serve as a microcosm for what happens throughout the universe? Consider the evidence we have examined. Intelligence is rare in Earth's history, evolved once unambiguously in 4.5 billion years. Complex life faced multiple near-extinction events. The window for preserving evidence of industrial civilization is surprisingly narrow. Beyond 10 million years, detecting past civilizations becomes increasingly difficult. This pattern suggests that if earlier intelligences had emerged on Earth, they would face the same fragility that threatens our own civilization. Climate shifts, asteroid impacts, volcanic eruptions, or self-inflicted catastrophes could end any civilization before it spreads beyond its home planet. The dinosaurs dominated Earth for over 160 million years, yet vanished in a geological instant when conditions changed. Our own species has existed for perhaps 300,000 years, a tiny fraction of the dinosaurs' reign, and our industrial civilization spans merely 2 centuries. We are newcomers with no guarantee of longevity. If earlier civilizations existed and failed to become spacefaring before extinction, they would leave minimal traces in the geological record. The absence of evidence would not necessarily mean they never existed, merely that they existed briefly on evolutionary timescales and vanished before making an indelible mark on the planet. This scenario would have profound implications for the Fermi paradox. If civilizations typically have only brief windows of technological sophistication before extinction, the galaxy might be littered with dead civilizations whose ruins have been erased by geological time. The "where is everybody" question might have a grim answer. They existed, developed technology, and died before managing to spread beyond their home worlds. Our own trajectory offers limited comfort. We have existed as an industrial civilization for roughly 200 years. In that time, we have developed nuclear weapons capable of destroying our civilization, altered our planet's climate in ways that could destabilize food production, and created numerous other existential risks. We are in a race between our growing technological power and our wisdom to use that power responsibly. If we fail, if climate change triggers societal collapse, if nuclear war erupts, if engineered pandemics escape containment, then 10 million years from now, whatever species evolves intelligence next might face the same questions we have explored in this narrative. They might search the geological record and find only ambiguous traces of our brief fluorescence. Despite the challenges of deep time preservation, certain types of information persist in stone with remarkable fidelity. Let us examine what the geological record actually tells us about Earth's past and the constraints it places on our speculation. The oxygen story. Around 2.4 billion years ago, oxygen-producing cyanobacteria transformed Earth's atmosphere. This great oxygenation event left clear signatures in the rock record: the sudden appearance of oxidized iron formations, rust, the disappearance of minerals that only form in oxygen-free environments, and changes in the types of organisms that could survive. This transformation occurred slowly over tens of millions of years, but it represents a permanent change in Earth's geochemistry that no subsequent event has erased. Any other major transformation of Earth's surface chemistry, such as industrial civilization releasing billions of tons of greenhouse gases, should theoretically leave similar lasting marks. The extinction events. The fossil record clearly preserves 5 major mass extinctions and numerous smaller ones. Each extinction event shows characteristic patterns: sudden disappearance of species, changes in the types of organisms that dominated ecosystems afterward, and sometimes associated geological markers like iridium layers from asteroid impacts or volcanic deposits from massive eruptions. These extinction signatures persist for hundreds of millions of years. If an ancient civilization had caused extinctions through environmental destruction, we would expect to see similar patterns, assuming we could distinguish them from natural catastrophes. The fossil record. Despite preserving only a tiny fraction of species that ever lived, the fossil record shows remarkable continuity in the evolution of life. We can trace lineages backward through time, watching features appear gradually through evolutionary processes. There are no sudden jumps where advanced organisms appear without ancestors, no mysterious gaps where entire branches of life seem to have been inserted into the tree of life. This continuity argues against scenarios where advanced civilizations genetically engineered life or introduced artificial organisms. The evidence shows natural evolutionary progression throughout Earth's history. The tectonic record. Plate tectonics leaves clear evidence of continental positions throughout geological history. We can reconstruct where continents were located at various points in the past by studying magnetic signatures frozen in rocks, matching geological formations across current oceans, and analyzing fossil distributions. This reconstruction is incomplete and becomes less certain as we go further back in time, but it provides a framework for understanding Earth's surface history. Any civilization that built on continental crust would need to fit into this framework. Their ruins would need to be located where continents actually existed at the time. The chemical record. Sedimentary rocks preserve information about the composition of ancient atmospheres and oceans through the minerals they contain and the isotope ratios of various elements. We can measure past CO2 levels, ocean temperatures, and even the chemistry of rainfall millions of years ago. This chemical archive constrains what could have happened in the past. Major industrial activity should leave detectable chemical anomalies if we know where and how to look for them. These multiple lines of evidence intersect and constrain each other. The rocks tell a consistent story of life evolving gradually, continents drifting slowly, climate shifting in response to natural forces, and extinctions occurring through asteroid impacts and volcanic eruptions. This consistent story does not absolutely prove that ancient civilizations never existed, but it makes scenarios involving globe-spanning industrial civilizations increasingly implausible the more evidence we examine. If the surface record is unreliable beyond a few million years, what about evidence that might be preserved underground? Deep mines, artificial caverns, or buried structures might survive longer than surface constructions. The deepest mines on Earth extend roughly 4 kilometers below the surface. Modern mining operations create distinctive features: straight tunnels, right-angle intersections, and chambers of specific dimensions designed for equipment access. These geometric patterns differ dramatically from natural caves, which form through water, dissolution of limestone, and create irregular, flowing shapes. How long would artificial mines remain recognizable? This depends on depth and geological setting. Shallow mines, less than 100 meters deep, would collapse or fill with sediment within thousands of years in geologically active regions. In stable continental shields, they might survive longer, but would still be heavily degraded within hundreds of thousands of years. Deep mines, 1 to 4 kilometers, would face immense pressure from overlying rock. Over millions of years, the rock would flow plastically, slowly closing any voids. Even if the spaces did not completely collapse, they would be deformed beyond recognition. Tectonic activity. In regions with active tectonics, any underground structures would be folded, faulted, and metamorphosed along with the surrounding rock. After millions of years of this treatment, even large artificial caverns would be transformed into ambiguous features. Sediment filling. Groundwater carries dissolved minerals that precipitate in underground voids. Over geological time, any open spaces would gradually fill with mineral deposits, making them increasingly difficult to distinguish from natural features. Some have speculated that deep underground nuclear waste repositories might represent humanity's most lasting legacy, sealed chambers containing radioactive materials that will remain hazardous for hundreds of thousands of years. But even these engineered structures face eventual destruction through geological processes. What about evidence deliberately preserved for future discovery? Could an ancient civilization have created time capsules designed to survive geological time? The most durable material we know is diamond, which can survive indefinitely under most conditions. Synthetic diamonds could theoretically be inscribed with information and buried deep underground, where they might survive for billions of years. However, finding such artifacts would require extraordinary luck, unless they were placed in locations specifically chosen to be accessible to future civilizations. Natural diamonds form deep in Earth's mantle and are brought to the surface by volcanic activity. Any ancient civilization's diamond time capsules would face the same geological forces and would be scattered randomly through the crust, with no way for us to predict their locations. The underground frontier, while potentially more durable than the surface, still faces ultimate destruction through geological recycling. No location on Earth remains truly stable over timescales of hundreds of millions of years. 70% of Earth's surface lies beneath oceans that average 4 kilometers deep. This vast realm remains poorly explored. We have better maps of Mars than of Earth's ocean floors. Could evidence of ancient civilizations be hidden beneath the waves? The ocean environment presents unique preservation challenges. Corrosion. Seawater is highly corrosive, especially to metals. Steel structures degrade rapidly in marine environments. Even shipwrecks from a few centuries ago are barely recognizable, reduced to mounds of concretion and rust. Marine life. Organisms colonize any surface submerged in the ocean. Wood-boring mollusks, barnacles, and countless other species rapidly break down and obscure human structures. Sediment accumulation. The ocean floor accumulates sediment continuously. Deep ocean basins receive constant drizzle of dead plankton, dust from land, and other materials. Over thousands of years, this sediment can bury structures completely. Plate tectonics. The ocean floor is geologically young, nowhere older than 200 million years. Oceanic crust forms at mid-ocean ridges, spreads outward, and eventually gets subducted back into the mantle at plate boundaries. Any evidence on oceanic crust older than 200 million years has been destroyed. Despite these challenges, the ocean does preserve some things remarkably well. Anoxic basins. In certain deep ocean basins where water circulation is limited, oxygen levels drop to zero. Without oxygen, decay slows dramatically. Shipwrecks in the Black Sea have been found in remarkable condition thousands of years after sinking, because anoxic conditions prevented wood-eating organisms from destroying them. Could ancient structures survive in similar environments? Possibly for thousands to tens of thousands of years. But even anoxic preservation has limits. Chemical processes continue even without oxygen, and over geological time, organic materials would still break down. Deep sea sediments, sediment cores from the deep ocean, preserve climate records going back millions of years. These sediments contain chemical signatures of past atmospheric composition, ocean temperatures, and biological productivity, any major environmental disruption caused by an ancient civilization should theoretically appear in these records. The absence of anomalous signals in sediment cores spanning millions of years provides additional evidence against recent industrial civilizations. While not conclusive, perhaps we simply have not sampled the right locations, it adds to the weight of negative evidence. Continental shelves. When sea levels were lower during ice ages, much of what is now shallow ocean was dry land. Human settlements from the last ice age now sit underwater on continental shelves. Could much older civilizations have built in similar locations? This remains possible, but continental shelves face vigorous wave action and sediment transport. Structures would be heavily degraded or buried. Finding such ruins would require dedicated searching of vast areas, work that is only beginning with modern underwater archaeology. The ocean keeps its secrets well, but not forever. Even the deepest trenches eventually recycle their contents through plate tectonics. The ocean floor offers no permanent repository for evidence of ancient civilizations. We have traveled through deep time, examined evidence from multiple disciplines, and considered scenarios ranging from plausible to highly speculative. What wisdom can we extract from this journey? First, uncertainty is not ignorance. The fact that we cannot definitively rule out ancient civilizations beyond about 10 million years ago does not mean such civilizations are likely or that scientific knowledge is unreliable. It means we understand the limits of what can be known given the evidence available. This represents intellectual maturity rather than weakness. Second, absence of evidence has meaning. While absence of evidence is not proof of absence, it does become increasingly telling the more places we look and fail to find what we are seeking. We have examined rocks from every continent, drilled ice cores going back hundreds of thousands of years, studied fossils spanning hundreds of millions of years, and analyzed the chemistry of ancient sediments. The consistent absence of clear evidence for ancient industrial civilizations cannot be dismissed as merely not having looked hard enough. Third, extraordinary claims require extraordinary evidence. The hypothesis that humans represent Earth's first and only civilization-building intelligence is the simplest explanation consistent with all available evidence. Alternative scenarios requiring ancient civilizations require us to explain why no unambiguous evidence has been found despite extensive geological and paleontological research. This does not mean we should stop looking or asking questions. Science advances by examining edge cases, investigating anomalies, and remaining open to unexpected discoveries. But openness to new evidence differs from assuming that lack of evidence equals hidden truth. Fourth, our own fragility should concern us more than speculation about ancient predecessors. Whether or not previous civilizations existed and failed, we know with certainty that our own civilization faces existential risks. Climate change, nuclear weapons, engineered pandemics, and other threats represent clear and present dangers requiring our attention and action. The geological record shows that extinctions are common, that climate can shift rapidly, and that even dominant species can vanish when conditions change. We have no guarantee of survival just because we have achieved technological sophistication. Indeed, our technology has created new vulnerabilities that did not exist in pre-industrial times. Finally, mystery enriches existence. Not everything can or must be known with certainty. The universe is under no obligation to make all of its secrets accessible to human inquiry. There is beauty in questions that remain open, in possibilities that cannot be entirely excluded, in the recognition that we are part of something much larger and older than ourselves. We stand on a planet 4.5 billion years old, looking backward through fragmentary records, forward toward an uncertain future, and outward into a cosmos that contains perhaps 2 trillion galaxies. Our civilization represents a brief candle flame in the darkness of deep time, remarkable, precious, and fragile. Whether we are the first or the latest in a series of intelligences that have graced this planet, our responsibility remains the same: to survive, to learn, to create, to preserve what we find valuable, and to pass on to future generations a world as rich and full of possibility as the one we inherited. Late at night, when the stars wheel overhead in patterns humans have watched for thousands of years, it is easy to feel the weight of deep time pressing down. Those photons entering your eyes left their stellar sources years, decades, or centuries ago. The ground beneath your feet contains rocks billions of years old. The atoms in your body were forged in the nuclear furnaces of stars that died before our solar system formed. In this cosmic context, the question of whether other civilizations preceded us seems almost trivial. Whether we are the first or the thousandth intelligence to evolve on Earth, we face the same fundamental challenges: to understand our world, to preserve our existence, and to create meaning in an indifferent universe. Yet the question persists because it speaks to deeper concerns about humanity's uniqueness and significance. Are we special, or merely the latest iteration in a series? Are we the pinnacle of Earth's evolutionary story, or just one chapter in a much longer book? Science cannot yet provide definitive answers to questions about civilizations that might have existed tens or hundreds of millions of years ago. The geological record becomes too fragmentary, the evidence too ambiguous, the alternative explanations too numerous. But science can tell us this: we are remarkable. We are the result of 4.5 billion years of planetary evolution and 3.7 billion years of biological evolution. We are made of star stuff, conscious of our own existence, capable of understanding the universe that created us. We can contemplate deep time, split atoms, cure diseases, create art, love, dream, and wonder. Whether we are the first to achieve these capabilities on Earth or merely the latest, we hold in our hands the possibility of a future stretching as far into time as the past we have explored in this narrative. What we do with that possibility will determine whether future intelligences, whether evolved from our descendants or arising independently after we are gone, will find evidence of a civilization that burned brightly and briefly, or one that learned to sustain itself across the geological ages. The rocks keep their secrets. Deep time erases most evidence. The ultimate truth about whether other civilizations preceded us may remain forever unknowable, but our own story is still being written, and that story, the one we are creating right now with every choice we make, is the one that matters most. The journey through deep time ends where it began, in the present moment, on a planet whose past remains partly mysterious, whose future remains unwritten, and whose current inhabitants hold the power to shape what comes next. We are travelers through time, standing briefly on a spinning rock that has seen unimaginable transformations and will see many more. We are here now, aware and wondering, asking questions that may have no answers, building a civilization whose traces may or may not survive into the deep future. And perhaps that uncertainty is exactly as it should be. Not everything can be known. Not every question has an answer. Not every mystery should be solved. We live in the question, and in living fully in that question, we create meaning sufficient for any lifetime, any civilization, any moment in the vast sweep of cosmic history. The stars continue their slow wheel overhead. The continents drift imperceptibly. The rocks remember what they can and forget the rest, and we, for our brief moment, wonder